All right, let's take a look at our PowerPoints for section 1.1. In section 1.1, we're just learning about problem solving. We learn about the strategies and the principles of problem solving. Our main goal is to understand Poya's 4 steps to problem solving, state and apply the fundamental problem solving strategies, apply basic mathematical principles to problem solving, and to use the 3-way principle to learn mathematical ideas. George Poya's problem-solving method is to step 1, understand the problem. Step 2, devise a plan. Step 3, carry out the plan. Step 4, check your answer. One of the problem-solving strategies is to draw pictures. Problems usually contain several conditions that must be satisfied. You'll find it useful to draw pictures to understand these conditions before trying to solve the problem. Example, each person in a group of 4 will shake hands with all the others. How many handshakes? So if we take a look at person A, they first shake hands with person B, then they shake hands with person C, then they shake hands with person D. Then person B is going to shake hands, right? Person B has already shaken hands with person A. So now they're going to shake hands with person C, then shake hands with person D. Now person C has already shaken person A's hand, person B's hand. So they're going to shake person D's hand. And then person D has already shaken hands with person A, person B, and person C. And so if you count the arrows, which they labeled for us, we have 1, 2, 3, 4, 5, 6 handshakes. Another problem-solving strategy is to choose good names for unknowns. It is a good practice to name the objects in a problem so you can remember their meaning easily. Example, one group of dance students is taking swing lessons and another is taking Latin dance. Labeling one group S and labeling another group L lets us see and remember that S stands for the students taking swing and L stands for the students taking Latin. So when we have good naming techniques, we can remember what we were talking about. Oops, that's my face. All right. Good naming techniques we use often. Another problem-solving strategy is being systematic. If you approach a situation in an organized, systematic way, frequently you will gain insight into the problem. Example, make a table showing available iPhone features. So our iPhone features are batteries, earbuds, and 8 gigabytes. And we could choose none. So if we choose none, then we're looking here. We have no battery at all, no earbuds, and not the gigabytes, right? If we choose one of the items, we could choose the battery, but not the other 2. We could choose the earbuds, but not the other 2. or we could choose the gigabytes and not the other two, right? If we choose two of the items, then we could choose the earbuds, the battery, but not the gigabytes. We could choose the battery and the gigabytes, but not the earbuds. Or we could choose the earbuds, the gigabytes, but no battery, right? Or our last option is all three choices. We have the battery, we have the earbuds, and we have the gigabytes. All of them. Here we have 2, 0. Nice. Another strategy is to look for patterns. If you can recognize a pattern in a situation you are trying to study, you can often use it to answer questions about that situation. Another strategy is try a simpler version of the problem. You can begin to understand a complex problem by solving some scaled down versions of the problem. Once you recognize a pattern in the way you are solving a simpler Once you recognize a pattern in the way you are solving the simpler problems, then you can carry over this insight to attack the full-blown problems. So often trying something simpler can give you insight into the harder problem. One of my favorite strategies is that guessing is okay. One of the difficulties in solving word problems is that you can be afraid to say something that may be wrong, and consequently sit staring at a problem, writing nothing until you have the full-blown solution. Making guesses, even incorrect guesses, is not a bad way to begin. It may give you some understanding of the problem. Once you make a guess, evaluate it to see how close you are to meeting all the conditions of the problem. So basically guess, but guess and check and guess again, right? Because if you remember, Poya's 4 steps are to understand the problem, make a plan, carry out the plan, and check your answers, right? Check your solution. Does your solution make sense? So in this strategy, guessing is okay. That gets you into the problem. But you have to go all the way through to the end and answer, did my guess actually work? And if not, be willing to go and readjust your guess. So it gives you insight. Another strategy is to convert a new problem to an older one. An effective technique in solving a new problem is to try to connect it with a problem you have solved earlier. It is often possible to rewrite a condition so that the problem becomes exactly like one you've seen before. That can sometimes often be like doing a simpler problem. Often the simpler problem is the one we've done before. Some mathematical principles. So those were all strategies to problem solving, and these are principles. So we have the always principle. When we say that a statement is true in mathematics, we are saying that the statement is true 100% of the time. One of the great strengths of mathematics is that we do not deal with statements that are sometimes true or usually true. The counterexample principle. An example that shows that a mathematical statement fails to be true is called a counterexample. Keep in mind that if you want to use a mathematical property and someone can find a counterexample, then the property you are trying to use is not allowable. 100 examples in which a statement is true does not prove it to always be true. Yet a single example in which a statement fails to make it false, let me reread that. 100 examples in which the statement is true do not prove it to be always true. Yet a single example in which a statement fails makes it a false statement. Be careful to understand that when we say a statement is false, we are not saying that it is always false. We are only saying that the statement is not always true. So false means it's not always true. That is, we can find at least one instance in which it is false. The order principle. When you read mathematical notation, pay careful attention to the order in which the operations must be performed. The order in which we do things in mathematics is as important as it is in everyday life. When getting dressed in the morning, it makes a difference whether you first put on your socks and then your shoes, or first put on your shoes and then your socks. Although the difference may not seem drastic, reversing the order of mathematical operations can also give unpredictable results. Note that we are not saying that it is always wrong to reverse the order of the mathematical operations. We are saying that if you reverse the order of the operations, you may accidentally change the meaning of your calculations. The splitting hairs principle. You should split hairs when reading mathematical terminology. If two terms are similar but sound slightly different, they usually do not mean exactly the same thing. In everyday English, we may use the words equal and equivalent interchangeably. However, in mathematics, they do not mean the same thing. The same is true for notation. When you encounter different looking notation or terminology, work hard to get a clear idea of exactly what the difference is. Representing your ideas precisely is part of good problem solving. So if we have a sign that looks slightly similar but slightly different than another sign, then they mean different things, right? So our first sign does not have an equal sign underneath. It doesn't have this little line, and the second sign does. So they must mean separate things from each other. The analogies principle. Much of the formal terminology that we use in mathematics sounds like words that we use in everyday life. This is not a coincidence. Whenever you can associate ideas from real life with mathematical concepts, you'll better understand the meaning behind the mathematics you are learning. The three-way principle. The three-way principle is an approach to teaching that we use a lot. So often we try to give a verbal explanation, an example, and draw a picture if we can. So we conclude this section with a method for approaching mathematical concepts that we illustrate in figure 1.6. So it shows three arrows pointing toward mathematical ideas. And one arrow stands for verbally explained, one arrow stands for graphically explained, and one arrow stands for explained by example. Whether you are learning a new concept or trying to gain insight into a problem, it is helpful to use ideas we have discussed in this chapter to approach mathematical solutions in three ways: verbally, graphically, and by example. Verbally, we can make analogies, state the problem in your own words, compare it with situations you've seen in other areas of mathematics. Graphically, you can draw a graph, draw a diagram, and by example, make numerical or other kinds of examples to illustrate the situation. So, what your main takeaway should be is that there are several ways to approach problem solving. The 4 steps that we try to follow is to understand the problem, devise a plan, carry out the plan, and check the answer. And those strategies, they can help us understand the problem and help us start to devise a plan. Once we start to do the math, quote unquote, do the math, that's when we're carrying out the plan. But we should always, always check to see if our answer matches the question. So it isn't just redo the math and see if you get the same answer, but does your answer make sense?